Alright, so in this PowerPoint we're going to go over a brief review of how power grids work, looking at how we can apply what we've learned throughout Unit 8 to different electrical components of electrical grid and to the overarching electrical grid itself. So, we may be familiar with the basic idea behind an electrical grid, that turbines inside of a power plant turn mechanical energy into electricity. How that happens, we'll take a look. And then we have these things called transformers. Transformers connect to power lines. Power lines connect to our houses. And then we have electricity. We may not know what the transformers are used for. And we may not know what happens inside with, say, circuit breakers inside of our house. So that's what we're going to learn about here is what specifically is happening inside at a greater level of detail inside of electrical grid. Okay? So first thing we're going to look at is turbines and electrical generators. Okay? So the purpose of a turbine slash electrical generator is to turn kinetic energy to magnetic potential energy and electrical potential energy. Okay? The main idea is that the source, wind, water, steam, etc., causes the turbine blades to rotate. The blades themselves are actually made up of loops of wire, while the walls are actually made up of magnets, like our motor that we made. Okay? As a result of the blades turning, there's going to be changing magnetic flux through the loops of wire, which causes current to run in the loops. Recall Faraday's law states that a changing magnetic flux through the loops causes current to run in our wires. So here's the inside of our turbine generator, simplified look. Okay, we have magnets right here, and then we have these spinning coils, which are the rotors. And then right here, the turbine spin shafts, that's where we'd have steam or water or wind turning the shafts themselves, okay? And then the changing magnetic flux that goes through the coils. The magnetic field itself isn't changing, but because the coils are constantly rotating, the magnetic field from the coil's perspective is constantly changing, and that results in a changing magnetic flux, and hence current is running in our generator, okay? So transformers, so now we have our electricity produced. So now we need to carry out our electricity to homes and cities and towns and so on and so forth. And that may require us to have a higher voltage than is initially produced by a generator, or perhaps a lower voltage, okay? So in order to do that, we need to be able to start with a circuit that connects to our generator and use that circuit to step up the to induce a voltage in another circuit, where in that other circuit the voltage can be higher. So for this purpose we have transformers. Okay, so the purpose of a transformer is to increase/decrease voltage in a grid for appropriate scenarios. What are those appropriate scenarios? We'll take a look at in a second. So the current produced by a generator travels to an electromagnet. So here's our generator, it's off screen, okay? We have the current traveling to our electromagnet right here, okay? This is what we call our primary circuit. The primary circuit is the input circuit, okay? The current is alternating due to the constant rotation of the turbines. So since the turbines are constantly rotating, our current is going to be alternating, meaning that it's going to be constantly changing in intensity and in direction. And as a result, as the current is alternating, that's going to produce an alternating magnetic field on the primary side of the transformer. Remember that a current in a circuit produces a magnetic field. That's Ampere's law. So a changing current is going to produce a changing magnetic field. Okay. So we have a changing magnetic field being produced on our left side transformer. So as a result, there's going to be a changing magnetic field passing through the coils on the right side of our transformer. And this changing magnetic field through the right side of our transformer is going to result in a changing magnetic flux through the coils on the right side, and that's going to cause current to run in the secondary circuit, hence aka Faraday's law. So as a result, we can have two disconnected circuits and use one circuit to power the other through a combination of Ampere's law, where the alternating current produces a changing magnetic field, and Faraday's law, where the changing magnetic field induces a voltage in the secondary circuit, excuse me. So here's a nice little GIF right here. It shows how things are working so far. We have our generator, except in this case, the wall is made up of coils of wire, and the rotors are made up of magnets. In this case right here, the changing magnetic field induces a changing current, alternating current. The alternating current causes a always changing magnetic field, and the always changing magnetic field passes through the coils on the right on the secondary circuit or secondary circuit, which induces a voltage and hence causes current to run in the secondary circuit. So the first type of transformer we have is what we call a step-up transformer, okay? So if current is high over long distances in wire, more energy is going to be dissipated due to the fact that the longer a wire is, the more resistance will be encountered in that wire, okay? However, we don't want high amounts of resistance. We don't want to lose a lot of electrical energy. We prefer to lose as little electrical energy as possible. So that means we want to minimize our current, okay? So the way that we minimize our currents is we actually maximize our voltage for a step-up transformer. The reason being is that in a transformer, voltage and current have an inverse relationship, okay? Now this is a little bit weird. We're not going to delve too much into this. You're just going to take this at face value. But the basic idea goes that there's a thing called electrical power we haven't gone over in this class. And basically the electrical power into a transformer must be equal to electrical power out by conservation of energy. Power is a quantity related to energy. And so power depends on voltage and current, so in such a way that if voltage increases, current must decrease, and then if current increases, voltage must decrease. So a step-up transformer, in order to minimize current, a step-up transformer maximizes voltage, okay? So the step-up transformer increases the voltage and thus decreases current and power line for long-term transmission. The way that this is achieved is simply through the number of coils. If we recall, the number of coils that a magnetic field passes through dictates the magnetic flux, so more coils means more magnetic flux, and hence when the magnetic flux changes, a greater change in magnetic flux. So if we have more coils on the right-hand side in our secondary component than in our primary component, then that's going to result in a higher secondary voltage, okay? And that's going to result in a decreased secondary current. Secondary being this part right here, primary being this part right here. So our secondary voltage is going to be higher than our primary voltage, and as a result, our secondary current is going to be lower than our primary current, okay? So basically, the number of coils dictates the voltage. The greater number of coils compared to the primary side, the greater the voltage, okay? And as a result of the voltage increasing, the current decreases, and this reduces energy loss in the electrical grid. So step-down transformers. The purpose of a step-down transformer is to reduce the voltage in a grid to a level safe for households, all right? There is another purpose for this, as we'll see in this bullet point right here, okay? But basically the idea is that a power line, well, there are two types of power lines, as we'll see in our end of PowerPoint diagram. The first type of power line for long-term transmission has 400,000 volts typically voltage. A shorter term power line has about 13,000 volts. Either way, it's really not safe. You don't want to be in contact with those things. So it's way too unsafe for households. Households run in the United States about 110 to 240 volts. Okay? So we need to lower from about 13,000 volts to about 110 to 240 volts. So a step-down transformer works to reduce the voltage in a grid to level safe for households, and as a result of reducing that voltage, it also increases current, which is good for appliances and households because if you recall from our study circuits, things that run on electrical loads like resistors, light bulbs, computers, televisions, typically require a good deal of current to be passing through. So we want to maximize current while minimizing voltage, okay? So a step-down transformer works to minimize voltage in the opposite way that a step-up transformer works, and that is by having less coils on the secondary side compared to the primary side. So we have lesser coils over here on the secondary side than on the primary side, and that results in a decrease in voltage, and as a result, an increase subsequently in current. So the next thing that we're going to come to is a capacitor, okay? Now granted, we are going to look at capacitors in the way they are traditionally seen in physics. In electrical grids, capacitors are used for a different purpose than how they are traditionally used in physics. But we're not going to worry about that here. We're going to worry about the way that capacitors are traditionally used in physics, which is as an electrical storage device, okay? So I'm committing a little bit of blasphemy here, but again, we're not going to delve too deep into the electrical engineering side of electrical grids, okay? So, what is a capacitor? So, let's say we want to store electrical energy for short-term, for a small amount of electrical energy for short-term purposes. Excuse me, for long-term purposes. Okay. Um, so, this necessarily dictates a capacitor. Okay. We could use a battery, but capacitors have several advantages over batteries, in that a capacitor necessarily isn't always going to be firing current. Okay, a capacitor, whereas a battery doesn't really have an on or off switch, a capacitor uh, can have an on or off switch that we can use. It's a little bit more subtle than that. And I'm really not hitting all the major points, so the physicist in me is kind of going, not too good. But for our intents and purposes, we don't need to dive too deep into things, okay? So, how does a capacitor work? So, a capacitor consists of two conductive plates in a circuit. What's going to happen is electrons are going to accumulate on the lead plate, which is right here. So, electrons are going to go from the negative terminal and accumulate on the lead plate. However, electrons cannot cross over to the other plate due to a gap. Some electrons can cross over. There is going to be some current. It's going to be a very weak amount of current. But for our intents and purposes, we can essentially treat it to the point that the current is negligible and that there's zero current between the two plates. Okay? So since there's zero current between the plates, there's no direct current flow due to the gap between the two plates. However, we can have indirect current flow in that electrons on the lead plate will repel electrons on the other plate. So the electrons on the lead plate are going to repel the electrons on this plate. So as a result, that's going to leave a net positive charge on the other plate, okay? Resulting in an indirect current flow, okay? Again, if we want to be technical, there's technically some current flow right here due to polarization, okay? The real way capacitors work is on polarization, but we're not going to delve too deep into things here, okay? So positive charge builds up on this other plate, resulting in electrical potential energy accumulating in between the plates, okay? We have this positive charge and this negative charge right here. They want to be with each other, but they can't. They're like Romeo and Juliet. Romeo, Juliet, and then we got the Montagues and Capulets right here. All right, but they can't be together due to the presence of the dielectric in between. Dielectrics are typically insulators. They prevent electric flow or electric current, okay? So as a result of not being able to be together, they have this electrical potential energy stored in between them in the gap between the two plates, okay? So as a result, capacitors store electrical potential energy for later usage. If you were to take this capacitor out and place it in another circuit, it provides you a brief burst of electrical current that you could use for specific purposes, okay? Oh, and that actually reminds me, digging back into the treasure trove of physics, the reason why capacitors are preferred over batteries is that capacitors can be used for what's called an RL circuit, or excuse me, a LC circuit, or if you want to get real fancy, an RLC circuit. Whereas batteries, since batteries provide a direct current, cannot be used for RLC circuits, okay? So capacitors do have some advantage in higher level physics, again, we can't go into in this class, okay? So capacitance, or the ability to store charge, depends on three factors. The first one is the area of the plates. Think of it like going to a buffet. The larger your plate is, the more food you can store, okay? So the more area that our plates have, the more charge can accumulate, okay? The dielectric material. So typically this gap right here is not empty, but it consists of a material, okay, that fills the gap and reinforces electric fields. The better the dielectric, the higher the capacitance, okay? So we're not going to go too much on the material side of things, but if you have a bet, and you're not going to be tested on this, so you don't have to worry about this, but if you have a better dielectric material, that's going to reinforce the electric field better, and that's going to result in a higher capacitance, and hence more electric potential energy will be able to be stored between the two plates. And then lastly is the separation distance. The closer the plates are together, the stronger the potential will be between the plates, okay? All right, and this goes back to the inverse square law that we're familiar with between electric fields and potentials and potential energy, okay? Although we're not going to work out the mathematics of all that stuff here. Although we certainly could if we wanted to, and we'd end up with the familiar equation of 1/2 CV squared equals potential energy of a capacitive parallel plate capacitor. So last thing we're looking at is circuit breakers. So now let's say we have our circuit fully set up. We have the generators, we have the transformers to step up and step down voltage as need be. We have the capacitors to store electrical energy for short-term uses in case of, say, let's say an electrical outage. But let's say now we have like an electrical storm that causes a surge of electricity in a house. Obviously, that's not good. We don't want that to happen. We can't just say assume ideal electrical grid. In real life, electrical storms happen, things happen, crap happens. So we need to be able to protect if there's a surge of current in a circuit to prevent electrical fires. So that's where circuit breakers come in, okay? And the circuit breaker, how a circuit breaker works is a circuit breaker works to open up a circuit and thus prevent current flowing in a circuit if the current exceeds a certain amount, hence preventing electrical fires, okay? The way that this circuit works is essentially we fight fire with fire, so to speak. We use excessive current against excessive current. How so? So the way that a circuit breaker works is as the circuit is closed by two contacts, one close to an electromagnet such as this, that's free to rotate and move, and then the other that's fixed in place and that can't move, okay? So what happens is that the current in the electromagnet produces a magnetic field by Ampere's law, okay? So as a result of that magnetic field, the magnetic field is going to attract this rightmost contact right here. And it's not going to pull it apart unless the magnetic field becomes too strong. How does the magnetic field become too strong? Well, that happens if the current reaches a sufficient level. Remember that the stronger the current, the stronger the magnetic field, and hence the strong magnetic force acting on the contact. So if the current reaches a certain level, it's going to produce a strong enough magnetic field to pull this contact towards the north pole of the magnet, and as a result, that is going to open your circuit, and that's going to prevent electric current from flowing. So as a result, a circuit breaker uses excessive current to fight excessive current, which is quite ingenious. It's a very novel application of Ampere's law that I always appreciate. So let's take a look at our summary here, okay? So we have a power plant. All right, generators make use of Faraday's law and changing magnetic flux through coils to convert mechanical energy to magnetic potential to electrical energy. All right, so now we have electrical energy. Now we need to step up this 12K volts to about 400K volts. So as a result, we use a step-up transformer where the alternating current in the primary side induces a changing magnetic field, and that changing magnetic field on the secondary side induces current on the secondary side. On the step-up transformer, the current is lowered and the current is minimized and the voltage is maximized. So now we have 400K volts and we have current minimized to reduce power loss and energy loss. But now we need to step down this transformer to a more appropriate level. So now we use a step-down transformer, which was the opposite of a step up. So now we have less coils on the secondary side than the primary side. And we repeat that process as we go from 13,000 volts to 240 volts. And then lastly, in order to prevent excessive electrical surges in the house, we have a circuit breaker here, which if the circuit breaker opens, you will need to physically reset if the circuit breaker opens. All right. And this is our electrical grid system, essentially how it works, nuts and bolts, at a more detailed level.